Great. Okay. All right. So good afternoon, everyone. So for the next few minutes, what we're going to do is to give you an overview of the GeoSciML, JSON, and vocabularies work that we're going to be doing at this code sprint. So my name is Gobe Obona. I work for the OGC, and I'm going to be supported on this lightning talk by colleagues Alejandro Villa, also from OGC, and Ed Lewis from the British Geological Survey. And I believe we have Johannes Eschdorf from Interactive Instruments Online. And I'm not sure if Clemens is on there, but Clemens is also from Interactive Instruments. Let's just get started. So effectively, we'll cover an agenda that looks like this. We'll go through some background, describe the GeoSciML logical model and aspects of the basic requirements class, and then we'll talk about the work, specifically the technical work that we're going to be doing, specifically development of the JSON schema files, as well as some work on the GeoSciML vocabularies. So if you're not familiar with GeoSciML, let's see if I can minimize the screen, or at least to move this out of the way. Okay, so if you're not familiar with GeoSciML, it's the geoscience markup language. It describes a logical model for how you represent geological or geoscience data. And the current version of the standard includes rules for how you encode that data using GML, the Geography Markup Language standard. And it covers a broad range of topics, but all firmly within the geoscience domain. So geological map data, geological timescales, boreholes, metadata, etc. And it has been around for quite a while. It has been implemented across the community. And within the OGC, so in terms of standardization, it has been standardized by the OGC and published by the OGC. However, the OGC has done that together with CGI. So that's the Commission for the Management and Application of Geoscience Information, which is part of the International Union of Geological Sciences, I think. Is that okay? Cool. Yeah, IUGS. In fact, CGI started GeoSciML and then brought OGC in sometime later to collaborate on the standardization. So it is well and truly a community-built standard. So this is the timeline. So this is the timeline from when it was initiated back in 2003 and right through to more recent days. So in 2003, CGI started work on the specification or thereabouts. And then the big jump, I suppose I can call it, refer to it as the big jump, was when the One Geology initiative took place. That initiative basically brought together several geology or geoscience stakeholders and agencies from across the globe, got them to collaborate on quite a number of initiatives within that One Geology brand. And GeoSciML played it played a role within that, a key role. So that probably had one of the biggest impacts in helping to advance that vision of having a common standard for the geosciences. And then 2012 version 3.1 was released. That triggered thoughts around standardizations within the OGC. So CGI brought OGC into that process around that time. So 2013 to 2017, leading to release of version 4.1, which is the current version. And 2017 September, from what I recall, there were some discussions at the OGC member meeting, which was the technical committee meeting, as it was called back then, around alternative encodings for GeoSciML. And one of the encodings that was being considered at the time was RDF XML. But the main thing there was that already the community had identified a need for alternative encodings for GeoSciML. So that has led to to one of the key things that we're looking at this year, this code sprint, which is a JSON encoding for GeoSciML. So I don't know if I've missed anything from the timeline, and I don't know if there's anything else, any other key events that you may want to highlight.
No, nothing drastic. One geology was the idea that you'd have a global geology map, and you'd be able to then the data would be interoperable with each other. So if you had data from France, Switzerland, Germany, you could then look at it all the same place and understand what someone was calling basalt, everyone else was calling basalt, kind of thing. Yeah. So that was a massive project. Then since then, there's been various other more local initiatives that are similar. So in Australia, where they've got federated geological surveys, they obviously have the different states, and they need to share that data with each other and be able to map the geology across the state boundaries for mining, oil and gas, etc. That they use GeoSciML for that, and that's the same in Canada. And there's a EU initiative that's similar. Yeah.
Okay, cool. Thanks. Okay, so if you're wondering why we're interested in developing a JSON encoding for GeoSciML, there are quite a number of reasons. So one of the reasons is pretty much captured on this slide. So this is a graph created from Google Trends, a service offered by Google, which tracks the number of searches or number of queries for various terms on Google over the years. So we have on the left-hand side, May 2021, and then, May 2021, and then at the far side, we've got November 2025. So we've got approximately 5 years of data there. The orange graph is, so that is JSON. So the number of queries or terms related to JSON that have been ran on Google in that period of time. The one at the bottom, the one in bluish green, is XML, or a number of queries related to XML that have been run on Google. And then in terms of the axes, so you can see with XML, it's been about it's been about 40 or so queries every 2 months. So that is on the left-hand side. And then, whereas with JSON, it was about 80 queries. And then the number for JSON basically shoots up around November 2021, reaching about 130 every 2 months or so. So you can see the difference, the level of interest. But then, of course, on the right-hand side, you can see that it starts to reduce slightly, but it's still high. It's still much higher than XML. So this kind of gives you an idea of the level of interest in terms of JSON from across the web, and why it's a good idea, to look at a JSON encoding for GeoSciML. But that's just one of the reasons. The other reason is efficiency of JSON. This is a screenshot of a city's data set. So basically, I think it originated from GeoNames actually, and so an export of the city's data set in GML that gave us a file, a 62 megabyte file. GeoJSON gave us 39 megabytes. So one of the reasons really is efficiency. So if you're working in an environment where bandwidth is a concern, then this is one of the things that you'd need to think about. For instance, if you're working in the field, maybe you're conducting some geological surveys, in some far away place or some place that doesn't have sufficient communications bandwidth. This is one of the things that you would consider. So that's one of the reasons. And then perhaps the final reason is, so we had a look at AI platforms, and when you look at the web, when you go through the web, you'll get all sorts of views as to which encoding is more ideal than the other with regard to AI platforms. So we thought, well, wouldn't it be a nice experiment to ask the 3 most popular AI platforms out there, which is better for AI platforms, XML or JSON? I won't name the platforms, but these are the responses that they basically said, truncated, just to be concise. So one of the platforms said, both have their place, but JSON wins for most AI platform use cases. And then the other one said, for most modern AI platforms, JSON is the default and best fit because, and then it gave some reasons. But a third platform said both JSON and XML are valuable for AI platforms, but they excel in different areas. JSON is generally superior for speed, while XML is increasingly favored for structuring complex prompts and LLM applications. So I thought, actually, these make sense. These are basically a summary of what you get when you review all the various opinions on the web. So there you have it, 3 reasons why it is a good idea to explore a JSON encoding for GeoSciML. So where does that take us? Well, so GeoSciML as a standard defines a logical model. It therefore follows some of the fundamentals of data modeling, in the sense that you start off with a conceptual model, you then move on to a logical model. That logical model is translated from the conceptual model, and then ultimately you arrive at a physical model, which is effectively translated from the logical model. So what this means is that you have the logical model specified in the GeoSciML standard, but then you have the option of physical models, a variety of physical models, perhaps one being in GML, another one being in JSON, perhaps in the future, another one being in GeoPackage. But this approach means that you can get all the benefits of the conceptual model without any limitations of any specific physical model. So these are pretty much the fundamentals that that all the data models that we work with tend to follow. So zeroing in on the GeoSciML logical model, so zoning in into for going deeper into it. It's organized into six packages, and those 6 packages include GeoSciML Basic, which identifies the core geologic features. There's also the GeoSciML extension, which provides a detailed description of basic features, which adds additional properties and associations to those classes. Then there's GeoSciML Geologic Age for representing geologic time. And then GeoSci Borehole, as the name suggests, this is more tailored towards boreholes and logs and drilling. And then GeoSciML Laboratory and Analysis for all of those analysis tasks. And then GeoSciML Lite, which offers a simplified alternative implementation of the conceptual model. So 6 packages. the focus for this code sprint is GeoSciML Basic. And if we have a closer look at what's inside GeoSciML Basic, we'll see that it has a sub-package for Geology Basic, collection, geologic event, geologic structure, geomorphology, and GeoSciML data types. So it's literally the fundamental and foundation part of GeoSciML. So this might be a bit difficult to see from over there, but so this is a view of Geology Basic. Please do interrupt me if I miss anything important. So this is a view of, it's a UML model of Geology Basic. So one of the packages in GeoSciML. Sorry, one of the sub-packages in the GeoSciML Basic package of GeoSciML. So in there, what you can see is, there's a geologic feature, which provides effectively the foundation for many of the other classes, or many of the other feature types. Then there's geologic unit, composition path, and you can also see in there the key attributes of those feature types. In fact, the attributes of those feature types, as well as the relationships. So you can see that these are effectively the foundation feature types on which a data set represented using GeoSciML would be described. And then there's the collection sub-package. The key thing about the collection sub-package is that it makes it possible for you to retrieve a feature collection, for instance, from a web service or an OGC API, for instance. So you have the collection, but then you can have items within that collection, and each of those items has got a number of additional features that it can represent or that it can include. Then there's the geologic event. So as the name suggests, this particular group of feature types is therefore representing events. So you've got not just space, but you've got time as well, or elements related to time included in there. You've got, yeah, there we go. So you've got even the numeric age as well. So there's quite a lot of information in there that is that associates a geologic feature with literally with an event. So it is one that will be naturally very important for any implementers. And then there's geology structure. On there, you've got foliation, folds, contact, and a few others. So this is another very important one. And then, of course, geomorphology, which you would expect, given the focus on geology. So you can see here that the geologic feature type provides the basis for the geologic unit and geomorphology feature classes, and the geomorphology feature type has a couple of subclasses or sub-feature types underneath it as well. And then you've got the data types, so planar orientation, linear orientation, which provide additional information to support any data set. So before we move on, I don't know if there's anything else that I might have missed from that set. Anything worth highlighting from that set? Okay, all right. Here none. So there are dependencies between the GeoSciML basic package and other standards within the OGC standards baseline. For instance, in fact, let me say the dependencies and opportunities. So the current standard obviously uses ISO 19107, or it imports ISO 19107 in terms of the logical model, and as well as the general feature model. It also imports SWI Common version 2. Now, since the standard was developed, as I said, when the standard was developed, GML was the encoding adopted for GeoSciML. Now we're looking at JSON. So a number of opportunities have come up, one of which is JSON-FG. So one of the considerations for this work in the code sprint is how we might be able to leverage JSON-FG within that, within that encoding. But the other recent development is SWI Common 3.0. So SWI Common 3.0 is a JSON encoding of the SWI Common data model, whereas version 2.0 offered XML, 3.0 offers JSON. So there are some JSON schema files there. So this potentially gives us an opportunity to leverage that as well. So that's one of the considerations that we'll think about during the code sprint. And then how we're going to develop it, we're going to apply the best practice for OGC UML to JSON encoding rules, which is a document that was adopted and approved by the technical committee with guidelines and rules on how you represent a logical model that is in UML, how you turn that into a JSON schema, or into a series of into a JSON encoding effectively. One of the tools that we'll be using is shape change. Many of you might have already come across shape change in previous OGC initiatives. It's an open source tool that has been used by a number of initiatives to support the transformation from a UML representation of a logical model to either a JSON or XML representation of that model. And we're open to experimenting with AI as well, where appropriate or where useful. So one of the things that we might look at, or that we will look at, is whether or not AI can help speed things up here and there. The key thing, of course, is not to get overloaded with having to to tidy up all the hallucinations that might come from using from an AI. So we're looking for a balanced approach, shape change primarily, and and if useful or where appropriate, AI to help with the process. And then we've got GeoSciML vocabularies. So I'll be really quick. So the other aspect here of this work is to prepare and register the GeoSciML vocabularies within the OGC definition server, also known as Rainbow. So the GeoSciML vocabularies were published by CGI. They are at geosciml.org, and they basically take terms from the GeoSciML standard and organize them into approximately 35 collections of terms. They are encoded in RDF Turtle and published on GitHub. You can see some screenshots from there. So the idea is to take those and prepare them for registration on the definition server. There are some technical considerations involved, and I don't know if you want to just say a few words about those regarding the IRIs and OpenGIS, etc.
should I do it from here or do I move to?
Well, the mic is right there.
Okay, cool,
Yeah,
cool,
yeah.
perfect. So yeah, so there are basically
Yeah.
we Ed and I discussed this already, but there are basically two potential approaches. One is we upload, we import the data as is. So basically using the same URI namespace that is currently published, or we mint, so to speak, identify specific identifiers under the OGC namespace. That's usually 3ws.openjs.net. And we create links to the already published resources. We opted, I mean, unless there's any reasonable objections, we opted for the second option. So we'll be creating, let's say, some sort of mirror version of the data that's already published and under the OGC namespace. And I think that's the most important technical aspect. So the other thing is, how will we maintain this synchronization between the regional data and our mirror? I'm actually working on that right now, so that we can have some automatic way of doing that without human intervention. And that is mostly it. Then it's a matter of right now we'll be doing it. We'll be publishing all of the data in on our development instance, and once we have a proper with a temporary namespace, OpenJS namespace, and once we have a proper namespace for not only for GeoSciML but for Earth Resource ML, which we also agreed that should be part of this exercise as well. Once we have a proper namespace for those two, we'll do the proper URI mappings, but I think that has to go through the naming authority and all of that. But basically, that's the plan.
Okay, that sounds good. Sounds good. Thanks for that.
What's similar issue? Not issue challenge, but with Inspire as well. So Inspire do the same thing, and they mint their own URIs, but it's the same vocabularies. So Inspire geology descriptions, they're the CGI ones.
Okay.
That's good.
Cool. Okay, thanks for that. So yeah, so how to get involved? So we have Johannes online. He's going to be working on the JSON schema files. Johannes, are you online?
Yes, I'm here.
Okay,
Hi.
great. Hi. So Johannes is going to be working on the JSON schema files. So he's going to be doing that remotely. But because we're obviously within the same virtual space, we'll be able to to keep in contact with Johannes. So what we'll probably do is at later on, well, at the end of the day later on today, there's a daily brief back. So Johannes, if you could please give us an update on progress later on today. I think it's at 5 o'clock. I think it's 5 o'clock our time, which is probably, I think that's 6 o'clock your time. So just a really brief update on that, and that will help to keep everybody up to speed. And then Alejandro will do the same regarding the vocabularies as well. So is there anything else that I might have missed, Johannes, regarding the JSON schema approach work? Sorry.
No, sounds good.
Okay. All right. Thanks. Okay. So and if anybody has any questions regarding GeoSciML, there's a lot of expertise in the room. So please do feel free to ask. If you're not sure about any part of the standard or the logical model, please feel free to ask. Ed is here today. So if you have any questions, please don't leave them until tomorrow. Ask the questions today.
And I did put a link on Discord and in the chat on the Teams meeting for the documentation that's written for one geology, which is really, really detailed and explains about the standard
Okay.
and how to implement the standard if you were going to make a web map service or web feature service that did it.
Okay.
And it's also got examples in there of geopackage encodings and shapefile encodings of GeoSciML Lite as a useful starting point.
Yeah. Okay, that's helpful. That will be very helpful. Okay. So how, if how everyone else can get involved. We are going to be writing a candidate standard for the GeoSciML JSON encoding. We'll start off the writing of that during the code sprint. So if you want to volunteer to help with that, with writing that, please do let us know. The other thing is, once we have the JSON schema files, even at the draft stage, we'd appreciate your help in in reviewing it, comparing it to the UML diagrams, but also creating sample JSON documents and validating those JSON documents with the JSON schema file. So there's plenty of work for everyone to get involved and to help out. And if you have any questions, feel free to reach out to us. If you are here in person, you saw who we are. Feel free to just walk up to us and ask us. If you're on Discord, those are Discord handles. Feel free to send a message and tag us to that question. And that's it. Any questions or comments? Yeah, sure.
One question.
Yeah.
Is there any specific reason you're not looking at JSON ALD, for example, or is JSON schema just gonna be like towards JSON encoding, or is there any plan for? Because I noticed that SOSA is also like more towards JSON ALD these days. So just asking, like, is there any specific reason, or is the tooling the problem?
No, it's not necessarily that there's a problem. So the current movement in terms of adoption, etc., is within the JSON schema part of the ecosystem. Whether OGC API standards or just even the encodings. So the current focus is to the current idea is to focus effort within that space. But as I mentioned earlier on in the talk, the whole conceptual model, logical model, physical model approach means that there's no limit as to how many encodings we can have. But we have to start somewhere. So for now, we focus on this, get it done, make sure that the APIs have got something that they can work on, as well as the JSON-FG implementers, they've got something they can work with. And then from there, I suspect the conversation will revert to which other platforms or which other technologies can be supported. And perhaps JSON-FG will be one of them. It might not be JSON-FG, it might be something else. It might be RDF shuttle. So, but for now, let's focus on this. There's somebody's hand is up. Yeah, who is that?
Hi. That's Steve Richard here. I was wondering, in terms of doing the JSON encoding using shape change, is there already a shape change configuration for doing the UML to JSON that we're going to use?
Johannes, please take that question.
Actually, I'm working on such a configuration right now. So I've got a first result on GeoSciML Lite, but I'm now continuing on working with the basic application schema.
Okay, so in terms of actually having some instance the schemas generated, we're still a ways away from that?
Regarding GeoSciML Basic, that application schema, yes. That is not available yet.
Alrighty, so, okay. Well, I'm offline. I mean, I'll be online here. The time zone is not very good for me here in Arizona, but I'd be happy to look at the schemas when there's something to review, and I can also generate instance documents using the existing XML examples we have as the basis.
Sounds great. Gobi, by the way, where should we post the any kind of draft JSON schemas to, should there be the GitHub repository?
Yeah, so we're setting up a GitHub repository, so I'll share that with you as soon as I have word from the infrastructure team that set it up. So I'll probably send you an email message within the next couple of hours if they've already set it up.
Okay, thanks.
Okay, thanks. So Steve, Richard, so thanks very much for volunteering. So I think that would be great. Your help there would be fantastic. So join us, I guess, when you're ready. If you have something that Steve can have a look at, or any other of the participants, please let them know, and then we can make some excellent progress.
Sure.
Okay. All right. Any other questions or comments? Okay. Well, thank you so much for your attention, and also for participating in the session. We're looking forward to doing some amazing and fantastic work with you this week. So until then, I guess, yeah, I guess thank you again, and see you later.